Hi, this is a video presentation for integrated project which involve 3 subjects: Reaction Engineering 1, Separation Process 2, and Process Modeling and Simulation. Before we move to the main points, please allow us to introduce ourselves. We are from Group 2J and my name is Joshua Kang.
Hello, my name is Abigail Bungan.
Hello, my name is Fakrul Sharizani bin Zulkifli.
Hello, my name is Noliana Raihan.
Hi, my name is Joshua Kang and I will be talking about the specification and proposed design for the 2 reactors involved in this project: Steam Methane Reformer SMR and Water Gas Shift WGS reactor. SMR reactor is designed for reaction 1 here to happen and then the product will send to WGS reactor for reaction 2 here to happen. The reactor selected for the process is multi-tubular packed bed reactor. This is because the reactor can produce the amount of hydrogen that we desire, which is more than 30,000 tons per year. It is also suitable for our case where the catalysts are in solid and the reactants are in gaseous state. Meanwhile, the suitable catalyst found to be nickel-based catalyst with Al2O3 species that can withstand high temperature. By using the red law for reversible reactions, we can obtain these 2 equations of rate of reactions where Ke is equilibrium constant. These equations are going to be used to analyze the strategy to maximize selectivity and yield. Selectivity is the amount of desired product over the amount of undesired product, where the amount can be represented by the molar flow rate, which is equal to the mass of catalyst times the rate of reactions. From the overall reactions, the desired product is hydrogen gas and the undesired product is carbon monoxide. Simplifying the equations and then substitute the red law equations in, this is the final equations that we can obtain. From the equations, we can conclude that the concentration of reactant need to be kept high while the product must be kept low in SMR reactor, and is another way around for WGS reactor to maximize the selectivity. From the equations, we also can see that the selectivity is proportional to K1 over K2, and from Arrhenius equations, we can say that the temperature in SMR reactor has to be high and the temperature in WGS reactor has to be low to maximize the selectivity. Yield is equal to amount of desired product over the amount of used catalyst. By using the same method, we can find that the condition to maximize the yield is totally different from the condition to maximize the selectivity. In our case, we should focus on yield because there is no any recycled stream in these 2 reactors. To complete the project, some information were taken from the reference, such that the optimum inlet temperature, the inlet pressure, bed length, steam to carbon ratio, superficial velocity, catalyst diameter, void fractions, and bulk density. With the information, we can then calculate the size of reactors required. First, we need to find the kinetic data where the rate constant is calculated by using Arrhenius equations. The equilibrium constant is determined by an equation given from the reference test specifically for these 2 reactions, and the absorption constant is found by using Van Hoof equations. The second step is to determine the mole fractions and molar flow rate using mass balance. The third step is to determine the mixture density for the stream entering each reactor, which can be estimated using this formula and their pure density in gas. The mixture density obtained is then used to calculate the pressure drop across each reactor using Ergun equations. With the pressure drop, we can then find the partial pressure of each species in each stream. By combining the ideal gas law and their stoichiometry relationship to form these final partial pressures formula formula that we can obtain by combining them. Next, the rate of reaction is to determine by using the rate of reactions formula for SMR and WGS that is given by the reference. And the step 7 is to calculate the mass of catalyst needed using the mole balance for packed-bed reactor. Lastly, divide the mass of catalyst by bulk density and we can obtain the volume of SMR reactor required to be 2501.27 meter cube and volume of WGS reactor to be 187 and 3.997 meter cube. With that, I pass to my group mate. Thank you.
In order to do mass balance calculation, we have done the calculation in backward calculation. So we start from the adsorption unit followed by absorption unit into the steam methane reforming. Our objective is to build plant design that can recover a value of 30,000 tons of hydrogen per year, which has a 99.99% purity. We have to find F1 to be further used in the reaction engineering report in this integrated project. The inlet flow of the PSA unit has been identified to originate from the outlet of an adsorption column that has been given based on the problem statement. Based on the newly calculated time TB new, we can identify the amount of hydrogen produced daily, which we also manage to get value of F3 from the outlet of adsorption unit, which is 3653 kg per hour. From an article, we managed to get the recovery percentage of 75% for this adsorption unit. By utilizing the shown equation, we managed to calculate the amount of hydrogen in F1 value, which is 72238.29 meter cube per hour. By obtaining this value, we can calculate the total flow rate of F1, which is equal to 38085.26 kmol per hour. Next, calculating the mass balance for absorption unit to remove carbon dioxide. Based on some references, we use the shown information to calculate the mass balance in this part. In this part, the value of outlet flow rate F2 is known from the inlet stream of adsorption unit. From the reference for SMR part, we managed to calculate the mole fraction of outlet WGS, which is also the mole fraction for F1 in this absorption unit. Then, we use the removal efficiency 85% to calculate the inlet F1 and mole fraction F2. By using rich loading capacity 0.5, we managed to calculate the flow rate and mole fraction of the other stream. This is the block diagram of SMR. From previous calculation, we managed to calculate F3 from the outlet of WGS. In order to complete the mass balance for this SMR, based on the article, it stated that the ratio steam to carbon is 4:1. By using the stoichiometric relationship, mole fraction entering and leaving stream can be calculated. For example, to find mole fraction for stream F1, we determine the ratio of CH4 to CO by the stoichiometric relation from SMR. For the other flow rate, we use the same method and the results are shown in the slide. After calculating the mole fraction of each stream, the inlet F0 for SMR can also be calculated. Thank you.
For the third part, which is hydrogen enrichment unit for subject CEB 2063, supervision process 2, this part will discuss about the special technique of the flue gas from a steam methane reactor which have previously been passed through an adsorption unit via adsorption method. In order to understand more about the unit design, we will discuss thoroughly about the type of adsorbent and its isotherm, the type of adsorption unit, design parameter of adsorption column, and also the regeneration method. Let's see on the choices of adsorbent that we have and what type of adsorbent is suitable for the process. We have selected 3 different adsorbent which are zeolite 13X, zeolite 4A and also activated carbon that had been investigated at ambient condition, which is temperature is equal to 25 degrees Celsius and also pressure is equal to 1 atm. In order to select the most suitable adsorbent for the adsorption of carbon dioxide, the CO2 breakthrough curve for each adsorbent were observed. Based on the slide, we can see that breakthrough time for zeolite 13X is the longer, and followed by zeolite 4A, and the shortest breakthrough time is activated carbon. This can be concluded by the higher the pore volume, the higher the pore diameter and surface area of adsorbent, the higher the absorption capacity. Thus, more amount of CO2 that can be absorbed, which that can lead to higher quality of hydrogen gas. This also can be proved by looking at the amount of CO2 absorbed by zeolite 13X is the highest. Based on the investigation, zeolite 13X has shown the most promising result to separate carbon dioxide from the gas mixture and fit well with PSA process.
Hello, my name is Abigail, and today I will be discussing about the type of isotope for zeolite 13X. Based on our researches, we have deduced that our adsorbent adheres to the Langmuir isotope, where the equation can be seen in our slide here. And in figure 3.4, it shows the shape of the graph of the absorption isotope for zeolite 13X. How did we verify this? Our group constructed a linear graph based on Henry's law, where Q equals to Kc. We extracted the equilibrium data of the amount of CO2 absorbed versus the CO2 partial pressure at 25 degrees. And after that, we constructed a linear graph for a Langmuir isotope and a Fredrich isotope. In the Langmuir isotope, a graph of 1 over Q versus 1 over P was constructed. Meanwhile, in the Fredrich isotope, a graph of log Q versus log P was constructed. Based on our findings, the Langmuir isotope shows more linearity compared to the Fredrich isotope.
As for the design of adsorption column, we have chosen pressure swing adsorption as the type of adsorption process, or known as PSA process. While for the type of adsorption column, as we can see at figure 3.8, we have chosen two fixed bed adsorber for this PSA process. Therefore, design parameters for two fixed bed adsorber are as stated in the slide, where the height of the column is 1 meter, while the diameter of the column is 4.4 cm. In order to determine the empty-zag or mass transfer zone, we need to find TB, TS and also TD for the breakthrough curve of zeolite 13X. For the curve, the value of TB when C over C0 is equal to 0.1, value of TB is equal to 30 minutes, while the value of TS when C over C0 is equal to 0.5, TB is equal to 37 minutes. And lastly, for TD, when the value of C over C0 is equal to 1, the value of TD is equal to 49 minutes. By having this value, we can determine the height of unused bed, which represent the empty zag. The calculation to find the height of unused bed are shown in the slide, where the height of unused bed is equal to 0.19 meter. According to one of our article that we have found, normally the height of the adsorption column used in industry is about 1 meter to 33 meter. So we have assumed that the height of adsorption column for scale out purpose is about 3 meter. Hence, the new height of unused bed and new breakthrough point can be determined, which we get HB prime is equal to 2.18 meter, and also TB prime is equal to 104.7 minutes based on the relations shown in the slide.
Lastly, I will now discuss about the regeneration method. Why is this important? A regeneration method is important to reduce the need of new adsorbent, despite to reduce the problem of disposal of used adsorbent. Our group has decided to go for the thermal regeneration, and it can be simplified into a few steps. First one, the desorber unit will be heated up from 120 to 180 degrees Celsius, and after that, a shipping gas will be passed through from the bottom of the tank, and it will exit the tank at the top with the CO2 absorbed in the adsorbent. Why we chose this method is due to the fact that zeolite 13X does not degrade easily in high temperature, as it is able to withstand up to 190 degrees Celsius, and besides that, it also has a high thermal stability. Figure 3.8 shows the thermal stability of zeolite 13X.
So, the next part and the last part for this video is reflection part. For the reflection part, we have follow Graham Gibbs reflective cycle. So, this is some of the question for the reflection. The reflective cycle consists of description, feelings, evaluation, conclusion, and also action. The answer for the question can be obtained from the next slide. So this is the answer that we get for our reflection part. That's all from us. Thank you and have a nice day.